So all groups pretty much came up with this structure, which is good. This is an interpretation of 1,3-dimethyl-cyclohexane. Okay? There were a couple groups that tried to drop in a pi bond, showing a double bond. The problem with showing a double bond is that that means the ending of your name would change to "-ene". Since that ending says "-ane", it must be single bonds all the way through, so there's no double bonds. Okay? For anybody that actually said they wanted a double bond, do you want to venture or tell me why you wanted to put in a double bond?
Because that's where we would draw our horizontal and vertical line.
Why do you want a horizontal and vertical line? Okay, so what you're trying to do is use cis and trans as a label that we're used to seeing with double bonds. Okay, and what we're talking about is the rotation of that double bond, generating why we would get cis and trans things. And one of the things that we talked about when we talked about cis and trans, okay, that I got kind of cranky about a little bit, is that cis and trans is a relational term. That's it. If I want to actually name a compound, I have to use E and Z. And right out of the gate, we've got a problem. Because how are we using cis in this statement? We're using it as a name. Okay? So that is highly flawed. And the reason behind why they're using it as a name is kind of a half-assed argument. The argument is that, well, it's obvious what the cis and or trans is referring to, and therefore we are okay to use that language and we don't have to be using explicit nomenclature language. Right? That's the argument for this. Except that when we go through and look at everybody's structures, nobody's been able to define what that cis is about. Okay? Because when we talk about cis and trans, it was about a double bond. Well, there's no double bond, so what's the cis and trans in reference to?
The wedges and dashes.
It is going to mean we have to bring in wedges and dashes. Okay? But again, why? What is the cis and trans in reference to? Same plane of what? The ring. Okay? And this becomes a dangerous statement to kind of deal with. When we're looking at this structure, we've got a ring that we've drawn here, and we've shown those all as single bonds. We're making the assumption that all of those atoms are in the same plane. Dangerous, we'll see that in a second. If all of those atoms are in the same plane, and we now go through and pick any one of those carbons, what is the hybridization of said carbon? sp3, I only see 3 groups. There's an implied hydrogen. Okay, sp3. And if it's sp3, that means tetrahedral. That means I need to specify wedges and dashes to appropriately show the arrangement of those atoms relative to each other in space. Okay? So let's look at that first carbon, that hydrogen, or sorry, that red position, that hydrogen versus the methyl it's connected to, our black carbon. Since we're saying the plane of the ring is our reference point, the red bond and that black bond, our substituents, must be wedges and dashed. Which one's which? Is red wedged or is it dashed?
Both, either both.
At this point, it doesn't matter. There's no other external reference. I can label it whatever the hell I want, but I do have to label it. So what do you want to label it?
Double wedge.
We're just going to pretend he kept his mouth shut. Okay. Some people don't like the bond floating out there to nothing, so we can go with CH3 out there. Okay. So we just picked. That's what we just decided to draw. Okay. Not yet? Okay. So now, we've specified that wedge and dash, so we know where the hydrogen is relative to that methyl. Does it matter? I don't know. I don't know if it matters. Okay? The way I would know is by evaluating the entire structure. And if we continue to go around and look at the other structure, or the rest of the structure, what do we find? We find another carbon similar to our red carbon. Again, 3 groups of electrons, right? Hydrogen and my CH3. Since I've got those 3 groups, 4 groups. I've got tetrahedral, which means wedges and dashes. Does it matter now where I place the wedge and the dash? Yes. Now it's very important because I've already defined the red position. Now defining this blue position has to take into consideration where the red position was defined and that I said it was cis. Okay? What do you think I'm referring to as being cis? The hydrogens or the methyls? Why the methyls? That was a fast answer. They're a higher priority or higher atomic mass. Those are our primary focus. Hydrogens show up where? Everywhere. We don't care. That's why we imply them. We ignore them. Okay? So if I'm now looking at this cis, I want the methyls to be on the same side of the plane, and we defined the plane being the ring. Where's my red methyl going away because it's dashed, which means when I get to the blue position, it must also be away so that it matches and they're both on the same side. The same side aimed away. That's now cis. Why don't we use an absolute nomenclature system? Okay, because we can't use E and Z. E and Z is used specifically for words, double bonds. Okay, so we would need a new naming system for this. There is a new naming system. Do you want to worry about it yet? No, wait like half a week. Sorry, it comes up real fast. Okay, it might actually be pushed into the next unit. I'm not exactly positive where it falls, but it's right at the tail end of this unit. It is the RNS. Is that this unit? It's close. Yeah.
I think it's a little bit talking about this.
Yeah. RNS is now looking at those positions, our tetrahedral centers, and saying, does it matter where all the atoms are relative to each other in space? Well, in the case of the blue and the red ones, yeah, it does matter. But it's not going to matter in any of our other black ones. Why not? It has to do with the things connected to it. And ultimately, the number of distinguishable things connected to it. Take a look at the blue one. Can you tell the difference between hydrogen and carbon? Yeah, so that's 2 distinguishable things. Can you tell a difference between this carbon and that carbon? Okay. Verbally, as I talked about it, you might be like, well, no, it's carbon versus carbon. But you said yes because
There's 2 hydrogens and then 2 carbons.
this is a CH3 and this is a CH2. I can tell a difference between those carbons. So that's 3 distinguishable groups. Can I tell a difference between this carbon and this carbon? That was a real confident no. I like it. No, because it's a carbon, and they're both bonded to 2 hydrogens and another carbon. But this one's bonded to a carbon that has a CH3 connected to it, and this one's bonded to just a CH2. Can you tell a difference between those 2? Yeah. Which means that's 4 distinguishable things. And as soon as we hit that line of 4 distinguishable things, that's where the new nomenclature system comes into play, and that's where we deal with RNS. Okay? Do you want to worry about RNS right now? Good. I think I heard someone say yes. No. No. The answer is no.
Is that going to be on the exam?
RNS, I have to look to see when the video is. Yeah. Okay? And this, again, comes to content. Content's always going to keep coming. It's always going to keep coming. You will always be practicing and working on something. Okay? And you're like, oh, RNS, I'm going to suck at RNS. Okay, so you suck at it. You miss one question. That's not a big deal. Don't stress over it. Okay? But don't put all of this stress over, oh, this is way too hard. I'm just going to do miserable on this. Well, worry about all the other stuff that you've done freaking awesome at. Don't look at just the things you suck at. Acknowledge the stuff that you're good at. Okay? And make sure those get better. And if those strengths continue to get better, now you can work on RNS. Okay? Kind of, sort of? So cool. We've got our structure. Cis 1,3-dimethylcyclohexane. Did I answer your question, Andrew?
No.
Good. Okay, we didn't answer the question because the question asked.
What is the best low energy orientation?
Stop. Low energy. Does this say anything about energy? No. Okay? And energy becomes an interesting question and dilemma to manipulate. And ultimately, when we look at a drawing, let's double back out to a more simple structure. Actually, let's do this one. Because we saw these ones. Do you think one of these, structures is lower or higher in energy than the other? Okay, I've only heard one yes. How about the rest of the class?
Yes.
Yeah? Why? Okay. What's going to dictate whether something's high or low in energy?
Overlapping of
Overlapping of
atoms.
less atoms. The overlapping of the p orbitals is ultimately going to be the same all the way through. So it's not a bad idea looking at where your orbitals are. Okay? But what goes into orbitals? Electrons. What we care about are the electrons in a good place or a bad place. Okay, well, what makes good places and bad places? Let's look at the electron configuration for lithium. How many electrons does lithium have? 3, right? So electron configuration for lithium, 1s3. Why not?
Because one shell is 2 and another shell is...
Electrons can only occupy so much space. I can only fit 2 electrons in an individual space, which means I don't get 1s3. I get to 1s2, and then what happens?
2s1.
I eject that next electron to the next highest energy level. So our electrons repel each other. And if I try to put more electrons into one space, what happens? Some other electron's going to kick out. They're going to repel. So electrons want to repel away. They want as much space away from other electrons as humanly possible. And if we look at these two structures, our alkenes, we'll be like, well, there's no difference. Those bonds are all in the exact same plane. Those are all going to overlap. True, the bonds do all overlap with each other. But what else starts to overlap? The electrons on the substituents. And if I look at the bottom case where the trans, that carbon electron cloud overlaps or interacts with a hydrogen electron cloud. Does hydrogen have a lot of electrons to overlap with? No. What happens if we go up to the top one? That carbon electron cloud is overlapping with another carbon electron cloud. That carbon electron cloud has significantly more electrons than the hydrogen. You're putting more electrons into the exact same space, which makes the top one higher in energy or less stable. Good word choice. Okay? So what we're concerned about is how the electrons talk to each other and see each other in different forms. In this case, it was pretty straightforward because where are all the electrons? They're all in the plane of the paper. And when we shift to our cyclohexane, what just happened? We took all of those electrons, and now where are they located? Not in the plane of the paper. So now our viewpoint on where those electrons are becomes significantly more conflicted and more challenged to understand where they're all at. So what we would want to do is change our orientation on the molecule so that we could see where the electrons were located and see what kind of interactions could possibly come out of it. And ultimately, what we're going to discover we need to do is use... Yeah, we're going to have... Oh, we erased it. We erased it? Yeah, we did erase it. Too bad. The Newman projections. The Newman projections were ultimately created to show how the electrons in a bond interact with the electrons of another bond. Right? And it's that communication, or lack thereof, making it a more stable, lower energy, or less stable, higher energy state. That's really hard to see with a cyclohexane, so let's stop looking at the cyclohexane for the moment, and let's look at butane. Okay, 2 drawings. Which of these is more stable? Okay, are these different molecules? Okay, we're going to play with that in lab today. Okay, no, they're identical molecules. But one of these is effectively me standing on one leg versus standing on 2 legs. Okay, we're changing the energetic of what I'm doing and where those structures are. Okay, one might be more like I'm bent over backwards versus standing upright. Do whatever analogy you want to do. Okay, how do we see that energetic difference? Well, we would see that energetic difference by changing our viewpoint on the molecule. And if we change our viewpoint on the molecule for this top one, I'm going to eyeball in on this red carbon. That red carbon, whoops, we're going to make it a blue eye. You know your colors better than me. Okay, and I want to look at that structure from there, which means that red carbon is in front. What did we call the red carbon, or the front carbon? The small one or the big one? The small one, so there's a red dot. Where's the methyl group going? That CH3 is going straight up in the plane. Straight up from that red carbon. I then have that bond going backwards to the blue carbon, but that bond has disappeared from my view. I can't see it anymore, right? So all I could do is show my blue carbon as a circle and back. Where's the blue methyl?
Right behind the...
Straight up in the plane of the paper. Okay? And said very nicely, right behind the front methyl. What happens in the bottom case? Okay? Conveniently, never happens, but hey, sometimes. Okay? We kept that orientation the same. We go back to that blue carbon, and now where's the blue methyl? Straight down. Okay? Massively modified Newman structure. Okay? But this gets at the point. Which of these 2 is more stable?
Trans.
The bottom one is more stable because the bond, blue bond versus red bond, are occupying different planes. Whereas in the top case, they're occupying the same plane. Kind of, sort of? Okay. Because they have different energies, of course, we associate different names, and we can drill into the discussion in detail behind each of those. Okay? But for the moment, we're just going to say that, yes, we get different energetics. Well, how did I go from the top structure to the bottom structure? What did I do? I rotated what? I rotated the sigma bond. So we took the structure, and I just did whoop. Did not break the connection between the atoms. All it was a rotation. And that rotation takes me from a really high energy state to a really low energy state. Does that matter? Why is that going to matter, you think?
Because matter likes low energy.
Right? So cool, matter likes low energy. Why else do you think it would matter? What do we want to do with our molecules? We want them to react. We want to change their structures. And to understand how their structures change, we probably want to start with the structure that is most prevalent in solution. And so what we're going to draw is our lowest energy structures, because those are going to be the ones that are most likely to be present. And if I want it to react and do something with a higher energy state, I'm going to have to force it to make that change so that it can initiate. How can I force that rotation? Add energy. If I heat up the reaction, guess what? More things move, including bond rotations. If I don't want it to rotate, what should I do? Cool it down. It'll reduce that bond rotation. That said, sigma bond rotations are wicked fast. Okay? To the point that we really don't get to control them. They're just going to do their own thing. Right? And they're going to spin and flip pretty much all the time. Chairs are a little bit different, but chairs at least give us a manifestation. We go through and look at this chair. Can we rotate those sigma bonds? So that way, here we go, right? We got a chair, or not a chair, but a ring, right? Or was it Taylor Swift? It's not Taylor Swift. Who's the diamond? Whatever. What? Rihanna. There you go. Okay. Can I rotate my thumbs? Can I rotate without breaking the ring? Because as soon as I try to rotate about that, what happens? I have to break the connection. So when we think about rings, should rings be able to rotate? The whole structure can rotate. That's not rotating the sigma bond. We're talking about rotating a sigma bond. Can I rotate a sigma bond? No. Okay. Andrew said I'm full of shit, so let's see what happens. Okay. Let's push on this a little bit further though. What happened with our double bonds? Could you rotate double bonds? No. And when we couldn't rotate the double bonds, what did we invent? Cis trans EZ. Why can we use cis trans on rings? For the exact same reason we can use them with double bonds. Our rotations can't, air quotes, happen. Because Andrew's right. And I'm right. How can we both be right? Because Andrew's absolutely wrong. There is no way I can rotate about my thumbs, do a sigma bond rotation there, and maintain the ring. It's not going to happen. It is impossible. So Andrew is 100% wrong, but I'm right. But if I go to 6 carbons in a ring, can I rotate? Oh, so the amount of atoms in the ring changes your ability to do the rotation or not? Yes. Right? And with a 6-membered ring, I can rotate. Can I rotate all the way around? Does that look like a good thing that I just pulled off? Okay. As we're trying to force that through to get that rotation, if you bought the kit that I recommend, do not try this with your kit. Okay? If you're going to use the lab kits, feel free to try it, because worst case, you just break it. That's okay. It's ours. Okay? If it's yours, don't do it. But as you do it, what you'll find is you'll feel a whole hell of a lot of resistance as you're trying to push it through, because there's no way in hell it wants to do it. Okay? You can't rotate a ring all the way around. You can rotate the sigma bonds just a little bit. Well, does that little bit matter? Yes. That now doubles back to dealing with energetics. Well, the energetics that we're talking about, what did we say we cared about energetics? What did we have to look at? What did we have to look at?
Eclipse and staggered.
Eclipse and staggered, which were examples of Newman projections. So if we're trying to figure out energy, when we look at a cyclohexane, guess what we've got to consider? Newman projections. So there's my cyclohexane. Right? Did I build the same thing that you guys drew? Some people are like, yeah, of course. I see those CH3s going which direction? Away. Where are these CH3s going? Did we build the same thing? Watch carefully. Isn't that annoying? Yeah, 100%, the exact same thing. All we did was look at the molecule from a different viewpoint. You're responsible for that. This is why the model kits become so critically important, is that you understand what it's doing in three-dimensional space, and you start to draw the structures of these in your head from the model. Kind of make sense? Cool. We wanted energetics. We wanted to know about Newman, right? So this could be really weird. We have to look at it, and we have to look for our Newman projection. The Newman projection means a bond disappears. That was bullshit. I didn't see any disappear. Right? Well, that's because you have to look at it at the perfect angle. Do you see the bond connecting my thumb and my index finger? So somebody over here from the side was like, yeah, Mike, you can't see it. I can see it from my side. Okay, smart ass. Do you see it anymore? No, this is all based off of the very specific angle at which you are looking at the molecule. And so you have to be on that viewpoint to be able to process it. Kind of, sort of? Cool. So there's a Newman projection. Oh, dang it. Am I holding it the same way? Do you still see the Newman projection? You mean there's more than one Newman projection in a ring? Yeah. For every substituent, there's two. Okay? Which is really unfortunate, because if you drop it, and then you try and figure out where you were at, you could very easily be picking it up and starting at a whole new system. So you have to know the relative positions of those things to be able to get into lockstep with what's going on with them. Yeah? Cool. We feeling happy about that? Good. I know you didn't answer. Okay. So here's the fun part. Did I say it was going to get fun? With these two systems, we have it eclipsed or we have them staggered. Okay? And note, what were the bonds that I highlighted in my drawings? Did I look at any of the hydrogens?
No.
Why not?
Irrelevant.
They're effectively irrelevant. When we draw proper Newman projections, we need to draw them in here. But did I show any hydrogens in my model? No. So that's why we're going to ignore them. So what I want you to do, because what we care about is the substituent. So I want you to keep your focus on that carbon, and I will try my best not to drop it. I was going to promise, but I can't do that. Okay, that carbon, and I want you to tell me when you see the eclipsed or the staggered configuration. Sorry, not staggered, anti. And if you're wondering, like, Mike, I didn't see it. Why are you moving away? Give me more time. Give me more time. No. Is the eclipsed or staggered visible? No. Neither of them are visible. And I keep calling it staggered. Is the eclipsed or anti-visible?
Because it's 180.
It would have to be 180 from something. Okay? What's 180 from this methyl group? Where would I put my hand to be 180? Here? Is that what we care about?
No.
My hand's kind of big for the model. We take a look. The 180 is directly behind it, but is it connected to the same carbon?
No.
No. So where my hand is, right? It's not connected to the same carbon. My 180 needs to be here. Kind of get it? Is there anything there? Like I'm milking a cow. Right? No. There's nothing there. So it isn't anti. Well, for it to be eclipsed, what would need to happen? What would I need to see?
You rotate it.
No rotations from here. There has to be a bond where? Right here above. And there isn't one. So what does that mean? It's neither anti nor eclipsed. Could there be middle ground? How did I transition from being eclipsed to anti? How did we transition from this side view to that side view? What did I have to do?
Rotate the sigma bond.
I rotate a sigma bond. And if I rotate the sigma bond, what's it going to start to look like? Let's rotate the black one. So we'll leave the, actually no, we got to leave the front one alone. What's going to happen? That blue one's going to be there. And as I continue to rotate, it'll go down there, there, until it'll be perfectly down. So what we're talking about is that rotation of that sigma bond. What does this introduce? Not only do we have eclipsed and fully opposite anti, but we're going to get intermediate stages. Can you tell me a difference in energy between this purple intermediate stage and this soon-to-be black intermediate stage? Top one's higher in energy. Is that what everybody's saying for the purple one?
Yeah.
Yeah, everybody agree? Everybody's on board. Foreshadow. Foreshadow. Everybody's on board? Purple one's higher in energy? What did we not show? Which one's higher in energy? Son of a... You mean the hydrogens come into play, and I have to be aware of where they're located. Yes. Okay? So when we look at Newman, we can't just ignore the implied hydrogens. We also have to be aware that they're there, which is why when we look at the Newman projection, we see the massive, weird compass stabby thing of doom coming out of it. And you have to evaluate each of those intermediate stages along the way. And what you're going to find as you rotate from a high energy state, it's going to go low energy, and then what's going to happen? It's going to go high energy again as it overlaps the bonds in front, and then it's going to go low energy again, and then I'm going to break my arm and turn it the other way. It's going to go high energy and then low energy, high energy and then low energy. And so what you'll see if you looked at an energy diagram would be it oscillating up and down depending on the energetics of each of those interactions. Why does that become important for us? Take a look at our purple drawing that you said was high energy, and it turned out was low energy. Is it lower or higher than the eclipsed?
It's lower.
It's lower because the bonds do not overlap. Is it lower or higher than the anti?
They're the same. Or
I heard it's apparently floating somewhere back there. Did you? You're sheepishly looking away like you actually said it. What did you say? You would say higher. Why is this purple one higher in energy than the anti? You are so right.
the methyl groups.
The CH3s are closer to each other than they are here. That makes this one higher in energy than that one. Okay? Why is that important for us? Well, we didn't see any anti. We didn't see any eclipsed. But what do we see here? Maybe I should do that finger. Sorry. What you should be seeing is that interaction. Okay. So that methyl group is generating a higher energy interaction. Right? That could be bad. So maybe this is a bad representation for my drawing. Okay? But does this look anything at all like what we drew? No, why not?
Because we bent the rotated a little bit on the signal
It doesn't look like what we drew? Okay. Did everybody track that? Because that was insanely subtle. Nope, doesn't look the same. Doesn't look the same because we bent, we did blah, 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 and then all of a sudden it spun it around. And it went, whoa, now it does. What changed? Did I bend? No, what did I do? I changed your viewpoint on the molecule. That is all that is changing. And your interpretation goes from totally different to, oh my God, they're the same thing. That's nasty. Pay attention to the models. Kind of, sort of? Okay. So, the overhead view didn't help us see any of those energetics. What allowed us to see the energetics? The Newman projection. So guess what you should try and do?
From the side.
You should try and draw the Newman projection of a ring. And for those people being like, I really don't want to have to do that in lecture, don't worry about it. You don't have to do it in lecture. You'll do it in lab. So don't stress there. You're welcome. Okay? What did we say the sigma bonds could do? Like, I'm not sure we covered that, right? We said that sigma bonds in a ring, right, couldn't rotate, and Andrew was wrong.
Yes.
Yeah, we said that, right? Except then we also said the sigma bonds in a ring could rotate. And so if I try to rotate this bond and that bond, what's going to happen is this is going to rotate, right? And then that's going to, come on, jerk, rotate as well, right? No, all I did was rotate. We see that? Does that look the same as what we just had? Does that look the same to you? What looks different about it?
Swap the seat in the chair, or like the.
Okay, swapped makes it sound like I did some nasty bond breakage. Did I break any bonds? No, bond's not broken. So don't be I swapped.
You say flipped, but it's not actually
Oh,
flipped.
okay.
Okay,
Yeah,
well, it's flipped, but
okay,
it's
there
not.
we go.
It's not.
So it flipped. It flipped what? The chair. Okay, for anybody that feels remotely questionable on this, do you see a chair? So, Andrew's clearly hallucinating. Take a look at it from the side here. That's where my back is, because I'm going to recline. That's where I put my booty, and that's where I put my legs. Do you see my chair? When you say sure, it does not vote confidence. Okay? So yeah, we flipped the chair. Because here, if I sat in this chair, which direction do I face? Cool, I face that wall. But if I do, as you were suggesting, my chair flip, and I now sit in it, where do I face? Oh, it changed, and I face the other direction. This is one of the reasons why we call it a chair flip. Note, it is not flip the chair. No. I'm doing sigma bond rotations when we talk about chair flips. Okay? So why would we evaluate looking at the chair flip?
Changes the Newman projections.
Does it? Did we look at the Newman projection yet?
It went from straight up to the side.
Take a look at your magic methyl group. And you want to look for your Newman projections. Do you see a Newman projection particularly standing out there? And we'll now double back the other direction with the answer. Look at where my thumb is. And if you're still questioning it, you see the Newman projection now. Those two groups are opposite sides of that line. That looks an awful lot like the anti-configuration. Right? If I did this rotation, does that mean I no longer have this molecule? That's a hard question. Right? All I did was a sigma bond rotation. So it shouldn't change the identity. That's me just doing this. I'm still Mike, just cracking the back. Right? So let's evaluate. Do we still have the same structure? Are those CH3s still aimed away from you? And for the people saying yes, you're alone. Because I would argue the vast majority of people look at this and they go, I don't see them aimed away from me or towards me. They look like they're in the plane. And I would agree with you. I think it does look like that. One of our first assumptions was that the plane of our ring was all flat. So if we tweak our structure out of that chair into the flat, does it look like the methyl groups are now aimed away from you appropriately? Yeah. And if we go, shoot, was it this way? Nope, not that way, wrong way. Go back to our chair, and we're like, but I can't tell. I can't tell whether they're aimed at me or at me, at you, or away from you. There's another hole there, right? Where's that white ball aimed? At you, which means where's that aimed? Away from you. Where's this ball right here? I don't know, I can't see it. Where's the hydrogen aimed? At you, which means the methyl must be away. There it is. Okay? So back to the question, it said you need to draw the lowest energy. Okay? Well, this view is that view. Okay? So is that the answer? This view is also that view. Can you tell a difference in the energy from that drawing? No. Where are you going to tell a difference? When you turn at it and look at it from the side. Which is why you need to learn how to draw not the overhead view, that's what we've been doing here. You need to look at the side view, and the side view shows you a chair. And we look at the chair, where are those carbons? Straight up. We look at the chair and the chair flip, where are they aimed? Out towards the sides. Which then means, what do you need to learn how to do? Draw chairs. And chairs no longer have wedges and dashes, they imply three-dimensional shape. Yay. Your artist skills come to life. So, here's that chair. We're going to draw it together. And by together, I'm just going to draw it because we're kind of out of time. And you're just going to, I should not have pushed that button. Okay, so I'm going to try and look at it from your viewpoint and see how bad this is. I'm not going to sit on a table again because that's how I broke the last one. It's so rude to laugh at me, guys. Chair. So the first place I'm going to start is drawing two parallel lines. What I'm drawing is my seat, where I'm going to sit in my chair. Okay. Now what I'm going to do is imaginary. It's not imaginary now. I just drew it on there. Cut the structure roughly in half by mass. And I'm going to look at the right half or the left half. Which half do you want to look at? Right half. Good. When we look at the right half, which line is longer, top or bottom? Which line is longer, the top red line or the bottom red line?
The top red line.
I asked the question wrong. Which line is shorter? From the shorter line, I'm going to draw wherever direction it is. Since it's on the bottom, I'm going to draw down because it's on the bottom. I'll now connect my triangle. I go to the left half now. Which line is shorter?
The top.
The top one. Since it's on the top, I'm going to draw up. Connect my triangle. I now have a chair. Okay? If you've seen people do chairs like this, lovely, that's awesome, good for them. Knock it off. Draw it proper, and you'll get better answers. This goes back to the conversation that we started at the beginning of class. Make sure you draw your structures appropriately. This gets you better orientations. If we're now looking at where my methyl groups are located, I gotta dance around it a little bit. Okay. If if I'm looking at the methyl groups, it's really kind of hard to see. But my head part, okay, there is no methyl group there. If I come towards me, one carbon, this is coming towards me, all of this bottom part, is towards. If I come towards me, one carbon on the left, I have my methyl. So I need to draw a bond for my CH3 coming from that. It's really hard to draw that bond. Just like it was really hard to see which direction it was aimed, it's really hard to draw it. So don't draw it first. Draw the hydrogen. Where was the hydrogen? Straight down from it. Where do I draw the methyl? Right there. Okay. Where's the other methyl? Well, it was 1, 3. We call this 1, 2. There's 3. This is oriented with the structure as we've got it up on the table. So, of course, people in the video, what are you talking about? Knock it off. Okay. Where's the hydrogen? Aim straight down from that position. Straight down. Whoops. That's not what I wanted. It's going to be like this. I like to break it over the bond in front so that I can see that kind of aspect that it's behind. I'm trying to show in some three-dimensionality. Kind of makes sense? Where's the methyl group? Well, the methyl group is in behind all of this and overlapping everything. So we're going to be really hard to draw it. So what we do instead is we just say the methyl is here. Okay. Go for it.
So on one of the lectures it says second over is parallel. So that methyl group would have been drawn like this way?
I drew them all right, dude.
You did?
Yep.
Okay.
Yep. So what we didn't address, and I'll talk through it, is the difference between where the hydrogen is located and where the methyl is located. Because if we go through the ring flip, and you're going to do it in lab, you go through and do that ring flip and try and redraw the structure, you're not going to get the same drawing. What you'll get is this. That was a little sloppy. That was horribly sloppy. Okay? You'll get that as your ring flip. Okay? And what you'll note is that in the green structure, in the ring flip, those CH3s are following the point. What point? The point of the bond that makes them, right? If we look at the one we originally drew, where's the point? The point is aimed down in both of those cases. And what did we draw down following those points? The hydrogen. Okay? When you're following the point, you understand everything. Sorry. Thank you, Andrew. I saw the head nod. If we're following the point, what we have is what's known as the axial position. Okay? And then what Andrew was actually asking about is saying that I drew my CH3s here wrong. Okay? If we don't follow the point, we get the equatorial. There's 2 rules for drawing the equatorial. Spelled wrong there. Equatorial, it's not drawn axial. Which sounds kind of dumb, but that's kind of important. The point is following down, which means not axial is going to be up in this case. Okay? So my up, but now where up? Because I've got a whole lot of range that I could go up. Where is it going to be up towards? It's going to be parallel, I'm doing notations, cheats, to the second bond away. How do you count that second bond becomes the question that you're challenging. First bond, second bond.
Is it always clockwise?
Is it always clockwise? I don't know. Check the other way. First bond, second bond. What's special about those 2 bonds? They're parallel.
I see.
Doesn't matter which way you count around the ring, because when you draw the structure right, the bonds are parallel when they need to be parallel to each other to draw your equatorial correctly. And if we take a look at that top CH3, we'll number it out in 1s. There's the first bond, second bond, I'm parallel to that bond. First bond, second bond, I'm parallel to that bond. Okay? That's where we're going to end for the sake of people in lab, guess what we're going to start with? We're going to redraw this thing and clean it up a little bit and try again so we can see it a little bit cleaner. Okay? For those people that feel like, oh my God, I need more practice with this, then feel free to stick around in lab. I've got no problems with that. You can attend lab both days because we're not actually doing any wet chemistry. I'll pause the lab lecture. We're